Hello everyone, welcome to my presentation. I am a PhD student from Norwegian University of Science and Technology. I'm going to present a speech conducted by me, Kiran, and Marius. The research is titled Supervised Contrastive Learning for Generalizable and Explainable DeepFakes Detection. First, I want to give a brief introduction of deepfakes. The definition of deepfakes is the content generated by an artificial intelligence that is authentic in the eyes of a human being. For example, in this GIF, a woman left is doing a speech, and by using deepfake technology, it is transferred as hilarious speech. This kind of fake news or deepfakes will raise significant concerns and posing tremendous intimidations towards society. There is an imperative need for automatic detection networks towards false digital to contend with this threat. Deepfakes detection can be posed as a closed-set problem where the training and testing data are drawn from the same label and feature spaces. For instance, in this figure, the model is trained with images attacked by A and also tested by attacked A. However, newer deepfakes generation mechanisms make the detection algorithm unreliable and non-generalizable by degrading the performance of the detector so that the detectors are not able to detect unknown attacks, which is an open-set problem here in this figure. We make three key contributions in this research. 1. A new approach exploiting the contrastive feature space between non-manipulated and manipulated images is proposed for deepfakes detection. 2. Considering the generalization aspect of the proposed approach, we report the results in a true open-set scenario by using 3 known manipulation types for training and 1 known type for testing. The proposed approach is evaluated on all combinations of known training and unknown testing set, where the results positively affirm the proposed approach. 3. In an attempt to explain the performance obtained from the model, we analyze the features from a visual aspect using the heat map and UMap. Motivated by the observation, we identified the complementarity of our proposed model with another top-performing model based on exception. We employed supervised contrasting for our tasks. The structure is shown in this figure. The main idea of contrastive learning is to learn representations such that similar samples stay close to each other, while dissimilar ones are far apart. Supervised contrastive learning first performs 2 random data enhancement, including random crop with flip and resize, color distortion, and Gaussian blur on each input picture in the mini-batch to obtain 2 different perspectives of the picture xi and xj. The 2 representations obtained are sent to the base encoders F to get an intermediate representation hi and hj. A projection head G is applied to these representations for nonlinear transformation to obtain a projection representation Zi and Zj. We train the network, calculate the similarity between the images, and then calculate and minimize the cross-entropy loss of the network. For our experiments, we employed the Face Forensics++. It consists of original videos and the 4 attacks, deepfakes, face-to-face, face swap, and the neural textures. The first column represents the non-manipulated frames, and the 4 other columns present 4 manipulated frames respectively. The total set of videos from each set of pristine and manipulated sets are separated into 600, 200, and 200 for training, validation, and test in a disjoint and non-overlapping manner. Considering the problem of open set classification, where the testing videos are seen, we employed the original videos and the 3 manipulated videos in training for each case, and retain 1 unused manipulated set as the unknown set. For example, original plus DeepFakes plus face-to-face plus face swap referred as DF plus F2F plus FS. For a set of n known deepfake classes in the training set, say DF1, DF2 to DFN, and real videos are, let TPI, TNI, FPI, and FNI respectively denote the true positive, true negative, false positive, and false negative for the ith closed set class, where I belongs to 1 to C. So the closed set classification accuracy is the sum of the number of true positive and true negative divided by the number of the whole samples. A trivial modification is made on CSC to get true open set classification accuracy. Now I belongs to I to C plus 1. C denotes the number of known classes in training, and the test classes is represented by C plus 1. As long as the test class C plus 1 is classified as a manipulated class, we deem it as a true case. And the open set classification accuracy is shown as the last formula, where TU and FU respectively denote the correct and false rejection for unknown classes. We assert that the supervised contrastive learning can cluster different classes in a reliable way, which leads to the potential of this model in deepfake detection tasks because it's learning strategy. This figure shows the architecture of our proposed method. After the training data go through subcon model, the intermediate representation of each data will be produced and sent into a classifier to get final score for the authenticity judgment. The lower part of this figure represents the heat maps corresponding to the last layer of the proposed subcon overlaid with the different kinds of deepfakes. We note that the subcon focuses on silhouette of the face region where the manipulation exists. Our assertion of the subcon applicable to deepfakes detection is corroborated through visual analysis. Furthermore, we also do a similar analysis on the exception network as presented in the top half. It is evident that the exception network focuses on the region inside the face, such as forehead, eyebrows, and the eyes. The focus on heat maps on different areas of the face region clearly suggests the complementarity of the networks. This table represents the baseline result of the closed set classification accuracy, along with the open set classification accuracy, to empirically validate the proposed approach of subcon for deepfakes detection. The proposed approach performs with more than 93.47% average accuracy on all closed datasets, with an exception to neurotextures, where the accuracy results in around 85.94% on average. While the accuracy in detecting deepfakes as an unknown class is 78.74% in the true unknown class setting, while the same accuracy drops to 85.82% 47.55%, and 54.61% for face-to-face, face swap, and the neural textures, respectively. We propose to fuse these two networks to obtain a better decision because of the complementary nature. We simply resort to use the decision scores fusion from each network. The coefficient for the final score from exception is xco, and the coefficient for the final score from subcon is sco. This table represents the result obtained from the proposed fusion approach in comparison to the proposed subcon model and exception model. Our fusion model consistently performs better than a single model while reaching at least the lower bound of the performance of exception model in two cases. The obtained result with a consistent gain indicate the complementarity of our proposed approach in improving the generalizability. This is the UMAP analysis figure using the features extracted by the penultimate layer. The purple dots correspond to the manipulated images, and the red ones correspond to the pristine images. As noted from this analysis, the features from subcon are mixed and spread across, while the UMAP for exception indicates the clear boundaries between original and manipulated images. We further concatenate the features from both models, which makes the features of the manipulated images to cluster in the middle, indicating the impact on classification. We further benchmark our proposed approaches against the 4 other state-of-the-art work which address the open set problem in DeepFakes detection to provide a fair benchmark. As noted from this table, the proposed approach provides either better performance or, in some cases, provide comparable performance compared to existing work. The future works in this direction shall be devoted to a cross dataset instead of focusing on FF++. The future work will also focus on different fusion strategies such as feature fusions in addition to score fusion. In addition, employing the complete scene information, the background, or looking at the temporal differences in the video frames can further improve the performance. The choice of loss functions and the detailed ablation study need to be investigated in the future works. Finally, a model trained with single category secondary data such as ethnicity, gender, and age can cause the bias of the detection ability. So future work should aim to explore and conquer the precise mechanisms of these biases in deepfake detection field. Thank you very much for listening.